So the extra material are basically videos and the slides for the course. So if you guys go to the site again, and you go to modules, then you can find the WebAssign link. So you can just go here and open WebAssign there. I will just give you a link in here, there. So make sure you always allow pop-ups from here. And then, yeah, it will take you to WebAssign from there. Okay. Make sure you check the announcements. Normally there are announcements regarding any video or extra information I might want to provide during the course. Regarding the attendance is normally taken within the first minute of class, and then after, because especially due to connectivity, I might have to be double checking every now and then. And when it's in person, I'm probably gonna just hand in a paper so you can sign. So if you guys go to modules, you will find pre-recorded videos. So every class is gonna be recorded, and eventually I might use the videos from this class to update my site. These videos are almost 3 years old now. Now the material is the same, the topics are the same, the examples are similar, but given the quality of the videos and the camera, I probably will use these summer videos to update these videos, but you can still watch them. For example, today's class is basically here, right? You can just go in there and you can just watch this video. And it basically takes you through the entire class on what we're gonna be covering. All right. Now, keep in mind that because it's a summer class, I'm going to be summarizing a lot of the requisite skills. I will just do an example on vectors today. I will let you guys know what topics from the previous physics course you need to know or you need to review, like kinematics, Newton's laws, the concepts of energy and power. And then we're going to move on into our first chapter, chapter 15, which is the introduction to electrostatics. Now, because we have labs twice a week, I think that will help you guys a lot to reinforce concepts. For example, if we're talking about electric fields and electric forces today, we have a lab on Thursday about that. So, and if you had it today or you have it on Wednesday, then that will reinforce whatever we cover. In a normal semester, the labs are done weekly, only once a week. So even though that's okay, you don't have much chances of, doing a hands-on experiment regarding a concept from the lecture. So I will use that as an advantage, all right? Plus there is no pressure about an in-person quiz this week. So I will just go through the material and then you can basically go back to the recordings or the slides to attempt your first exam or your first quiz. So make sure you take a look at those videos, and then there are some slides and sample problems that I will probably be using in class to demonstrate some mathematical computations and concepts that we're going to be covering. So the attendance is just part of what we are required as from the college, but it's not graded, all right? Especially for a remote live or hybrid class, the attendance is not really counted or graded, but we still keep it as a record, all right? If you happen to be on campus, you can always come in because I will be doing all the remote live sessions from the room, which by the way, we'll have to change probably because there is not enough seats. There is 30 of you. So we're probably gonna have to use a larger room. But in the meantime, I'm using 115. So if you're around, you can just stop by today or Wednesday, okay? On Thursday, we're meeting for class. And if you have any questions about what's gonna be on the quiz, you can always ask that day. We also have a lab on Thursday, okay? The lab will be about electric fields. And I believe between today and Wednesday, plus the videos that I have here, should be enough to cover what we're gonna be doing that day in the lab. The lab is before class, so make sure you are there on time, okay, from 11 to 12:55. Okay, so going back to the syllabus, just to show you the grading system, and then we can start with the topics. Okay, so the final will be made by me, so don't worry about the departmental final. That's 20% of your grade. The free tests are 45% of your grade. None of those are dropped, but one of them will be online. So, I mean, that will give you the chance to, if you have, you know, a low grade, to increase it. Normally that's what happens. Quizzes are 15% of your grade, and assignments, the web assign, are 20% of your grade. That means this. Okay, so make sure that you complete these assignments as you go, because they will help you a lot to get a high grade in class. That's normally what I see in my years teaching physics here at Middlesex or other colleges, that web assign helps students to increase the GPA, especially if they complete it to 100%. Now, regarding web assign, there is a system I use, a grading system, where you can get between 80 and 100% in your assignment, and you still get 100%. All right. If your web assign grade is between 60 and 80, you get automatically 85%. And if your web assign is between 40 and 60, you get 70%. So that will help you a lot, not just to motivate you to do the assignments, but to actually work on the topics that are related to the lecture. Okay, and especially the online quizzes are going to be similar to the web assign, because I'm going to use the same material, the textbook. All right, the tests, however, are not going to be identical, but the topics and the level of the questions may be about the same. All right, the main difference between a test and a quiz is that tests are all short-ended questions. Okay, so there will not be, except the final, multiple choice questions on the big examinations. All right, that means test number 1, 2, 3, and the final exam. Now, these are tentative dates for the tests. All right, well, no, not even the 12. Probably this week will be test number 1. We'll see. All right, I'll let you guys know. It depends how much we have done in the course. All right. So don't follow these due dates. Actually, I want to see if there's something here. No, there's nothing there. Okay. If you cannot make it to an evaluation, especially these main evaluations, please send me an email. I already got emails about the final. So I will have to make accommodations, basically provide you guys a different final on a different date. That's fine, don't mind that, but let me know on time. Okay, let me know on time. I believe all these dates are wrong because they are based on a normal semester. So don't worry about this. Okay. And all the web assigns are there, and there is your extra credit. All right. Are there any questions?
So would the test be multiple choice or open-ended?
Open-ended. All the tests are going to be open-ended.
And the homework.
The homework are half and half.
The homework, do we need to show our work?
No.
And if okay.
No,
Thank you.
Homeworks are you type the answer or you mark the correct answer. So that's what I was saying. Quizzes will be probably like that. If they are online, they will be like that. Tests, however, they are not going to be like that. The same material, but the idea behind a test is to actually check if you understand how to get to the right answer. So there is partial credit, of course. But the goal is different on a test, for sure. Okay. Okay, where is this? So let's use this. All right. I think I got everybody that is in here. At the end of the class, please do not leave immediately. I will double check the attendance at the end of the class, okay? All right. So let's use this now to introduce or go a review, do a quick review on vectors, and then we can start with chapter 15. Okay. I believe. All right, so what I like to start every semester, even on a normal semester, is to do like a review on vectors and to actually tell you what topics you are going to need to review for physics 2. Now, you're going to be provided a formula sheet, and you can have your own on evaluations. But there are some concepts and equations that you need to remember. One of the first things you need to remember is the whole concept on vectors and kinematics. All right. So basically, what you guys did on physics 1 was introduce what a vector is and what a scalar is. So if I were to draw this, right, and you have this type of notation, right, you will immediately remember that that is a vector. A vector has two properties. It has magnitude and direction. So in this course, like in physics 1, we are going to be focusing on vectors on the plane. I can give you a vector on the x-axis, on the y-axis, and then you can tell its magnitude and direction if I give you a value. For example, here is your x and y-axis, right? The x-axis, the y-axis, and then you have a vector like this. You see the vector in there? So I can tell you that this vector has magnitude 3. So that's the magnitude of the vector. It can be 3 newtons, 3 meters per second, 3 meters, 3 kilometers. Well, those are the units. This is the value of the vector. That's the magnitude. So normally we say that the magnitude is labeled like this. That's the magnitude of a vector, right? Like the absolute value. It's always positive. It cannot be negative. So I will say that this vector, in vector notation, will be, so this will be 3 on the positive x direction. However, in physics or in mathematics, we also label this as 3i, where I is a unit vector on the x-axis. If I were to draw a vector on the y-axis, here, and I say it's a value of 2, this vector here is 2j, or 2 on the positive y direction. You see the hat in there? That indicates that it's a unit vector. All right. In some textbooks, what they use is a bold type of letter, right? To make the difference with the I imaginary number. I rather use this because it's showing you that it's like a arrow, a vector, unit vector. We call them unit vectors because they have magnitude of 1. So if I were to say, what's the magnitude of the vector I, that's equal to 1. The same with j, the same with k, right? Like that, and then this like this is also 1. Again, since we're only going to be referring to vectors on the plane, let's just stick with I and j. Later, we might have to introduce the third dimension, or we are going to have to introduce the third dimension. But for now, I want you guys to remember that. Now, adding vectors when they are in the x and y axis is not difficult. Like if I give you a vector like this, 5, and then a vector like this, 3, the addition of those vectors, right? If I were to add these vectors, it will give me 2 on the positive x direction, right? That's 5 on the positive x, or to the east, 3 to the west, or to the negative x direction. You add them like that, just subtract them. However, what happens if the vectors are like this, though? Let's suppose I want to add 3 and 2. They are making an angle of 90 degrees. So how do you add vectors that are not on the same direction? If they are making 90 degrees, that's simple. You guys should remember that from physics 1. If you don't, let's show you here. If you were to add the vector 2 there with 3, so 3 to the x-axis and 2 on the y-axis, right? And we're going to see situations like that in chapter 15. Then you should remember your parallelogram method, right? In this case, the rectangular method, where the resultant is this. What you should remember is that if it's 90 degrees, the resultant is a hypotenuse, right? Because these two vectors here can be moved there. So this is 2 units. This is 3 units. So the resultant vector, the magnitude of the resultant vector, is equal to the square root of 3 squared plus 2 squared, which gives me the square root of 13. That's the scalar. The resultant is a scalar, right? Can I have a vector answer for that question? Or what will be the vector sum? Well, we have to use the components, right? The component is 3, on x is 3, on y is 2. So the vector r, make sure you're taking note of this, is 3i plus 2j. See? In some questions, when they ask you about the force vector of 2 or 3 point charges, you may be able to write it like that, and that's fine. But in some questions, they might ask you to find the magnitude of this. The magnitude of this is this. So you just have to be careful, right? One is a vector, one is a scalar. Now, why is a vector actually useful? Because sometimes you also need to know the direction of this. What is the direction of the resultant? Which is that angle that I just drew there, right? This angle here between the resultant and the x-axis, that's the direction of the vector sum. And how do I find that angle? Well, I mean, if you remember your trigonometry, then opposite of an adjacent is the tangent of theta. So here you can say that the tangent of theta is 2 divided by 3. And how do I obtain the angle theta from that, right? The angle theta is basically the tangent inverse of 2/3. Now, this is when you have to use your calculator, right? In this course, you can use scientific or the TI-84 graphing calculators. Just make sure that depending on the question, you may need to use degrees, all right, to obtain the answer for that. So that's your direction of vectors, that's your magnitude, and that's your vector sum and your components. Now, is it always like this? Do we always get vectors in the x and y? Or do we sometimes obtain vectors that are given at angles on the plane? And the answer is that depending on the situation, you may have vectors that are not necessarily on the x-axis or the y-axis. So what do we do in that case, right? What do we do in cases where we need to break vectors into components, where we have to use our sine and cosine? So let's review that, okay? Basically, I'm going to give you now 2 vectors, and we are going to remember how to break vector into components. In the first chapter, and when we start doing magnetism, right, the way we introduce electrostatics is by introducing the vector electrostatic force and the vector electric field. And because those are vectors, we need to remember this. At least, how do we use the mathematics, and how do we break vector into components? All right. The main difference will be with the numbers, and I will go into that in a second. For now, let's show you what happens when I give you 2 vectors on the x and y plane like this, where one vector is maybe like this, and the other one is like this. All right, let's say this is 45 degrees, and this is 60 degrees. I'm going to give a value of this of 10 units, or let's use some units, 10 newtons, and this, let's say, is 20 newtons. All right. One of the things that I want you guys to have as well in your equation or formula sheet are the special triangles. There are 3 special triangles I want you guys to have. All right. You probably know at least 2 of those. The first one is the 45-45, which is this. (45, 45). That's like x root 2. So 1 root 2, 2 root 2, and so on. And the other one is the 30-60. So like this, 30 and 60. Again, that's 90 degrees. This is like x root 3 and 2x. Right? Those are the ones that you guys should know. The other one is the 3-4-5. that. 37, 53. This is like 4x, like 3x, like 5x. There are more, but those are the ones that I want you guys to make sure you have it with you. So it makes it easier to solve problems like this. So how do I break the vectors into components? And how do I find the addition of this? A and B. So if I want to find vector A plus vector B, right? What you will have to do is, since the vectors are not on the axis, but now they are making an angle with the x and y axis, you have to break each vector into components, add the components, and then find the answer of it. So the way you do this is by breaking the vector into components. So first we do that vector there, right? This is the adjacent. This is the opposite. So that vector here, or that component here, we say this is the AY component. And this is the AX component. The AY component will be 10 times the sine, right? That's the opposite. Opposite over hypotenuse is the sine of the angle. So we use that. 10 sine 45. And this will be 10 cosine 45. Now the sine of 45 is √2/2. Opposite over hypotenuse. So that will give me 5√2. And this will give me also 5√2. Why? Is the sine of 45 is equal to the cosine of 45. Now what about this? The same, right? What I do now is opposite adjacent. So this is your Bx. And this is your By. All right. This is the adjacent. So that will be the B cosine 60. The cosine 60 is 1/2. So we use here 20 cosine 60, which will give you 10. And this will be 20 sine 60, which gives you, well, sine of 60 is √3 divided by 2. √3 divided by 2. This will be then 10√3. So you can see you have all the components now. You have this, 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 and this. Right? Yeah. Vector A and vector B are going like that. So you can say that this component is to the north, this is to the east and north, this is also going north, but this one, because the vector is going like this one is going west. So you have two components that are going up, like this, and two components, one to the east, the other one to the west. So the ones that are in opposite directions, you have to subtract. And the one going on the same direction, you have to add. Pretty much what you do to find this value is you can find the vector resultant. Your resultant will be on X and on Y. On X will be 5 root 2 minus 10. Now, 5 root 2 is approximately 7. Minus 10 will be negative 3. So that means that there is more force going to the west than to the east. So you can say that this is negative 3I. I'm approximating, by the way. All right. And then this is 5 root 2 plus 10 root 3. 10 root 3 is around 17.3. We say 5 root 2 is approximately 7. So 17.3% 24.3. So this up and this up is approximately, you add them, 24.3 J newtons. That will be your vector resultant. I subtracted these two, because they're one like this, and I added these two, and that's it. All right. Now, what if they were asking you for the magnitude of that vector, right? Which, yeah, it's pretty clear. So if you want to find the magnitude of this, let's do it here. All right. So the magnitude of that vector there will be R magnitude. You do Pythagorean theorem, right? Square root of negative 3 square plus 24.3 square. All right. So if you were to use that, and for that you have to use a calculator, I mean, you could approximate it to like 585, the square root of that, which is probably around that. There, plus 9. Well, 599. So the square root of 599 is 24.5. So this is about 24.5. So that's the magnitude of this. And that's how you solve problems using vectors. Make sure you are taking note of the method. All right, how to break vectoric components, how to use the components, how do you add them, how do you write the answer, what's the difference between the magnitude and the vector form, because you're going to need it. Furthermore, what you're going to need to remember is how to work with scientific notation, because these numbers are appropriate when you are looking at mechanics. Physics 1 was all about mechanics, Newton's law, forces, weight, masses, speeds, displacement, distances, torque. But physics 2 is going to start introducing the idea of the charge of the electron. And spoiler, right? The charge of the electron is, well, magnitude-wise, is 1.60 times 10 to a negative 19 coulombs. So that's a very small number. So we need to use powers of 10. So you may very well have vectors with powers of 10. So as we go in the course, make sure that besides the understanding of this, you are comfortable using powers of 10. And not just in the calculator, but also in paper. And don't worry, because we're going to be doing examples on that, but those are the type of numbers we're going to be working on. Also, remember to review your concept of kinematics. I will say kinematics equations and work and energy. In chapter 16, we're going to introduce the electric potential energy of a set of charges. So the concept of work and energy and conservative forces is going to be brought back. And kinematics, where we're going to have at the beginning charges not moving, but then at some point we're going to have charges moving due to an external electric field. And that's what we need to remember. How do we find the acceleration of a particle? The kinematic equations, so make sure you have them with you, okay? And then your kinetic energy, potential energy equations, all right? Are there any questions before we start with chapter 16? Remember, all of this is being recorded and it's going to be posted online. But I just want to make sure that everybody is following the class. If somebody just joined, I went into the syllabus in the first minutes of class, so you can just go and take a look at it. I went over the grading system and I went over the web assign. Make sure you are registering into the web assign today after class. I'm going to be double checking that today. And actually, we're going to start covering chapter 15 now. So that will give us enough time to cover material that you can actually use to start your assignments. Okay? All right. So let's start with chapter 15. By the way, the book that we're using, if I didn't mention it before, is the College Physics from Survey and Buell. But the slides I'm using are based on the previous book that we had. And don't worry, because it's the same material, the same examples, basically. All right. Just in case when you go over the slides and you see something that is not really from Cengage, it doesn't matter. The sample problems are from Cengage. All right. Some of them have the answers. But let's go into this. If you have done the lab today on this, then you probably have seen this already. I will talk about this at the end of today or maybe on Wednesday. But what you're seeing there right now is basically what you're going to be doing on the first lab, is mapping electric fields between an arrangement of charges. Okay, that's one of the objectives of chapter 15, is to show you what is an electrostatics, what is an electric field, and how it's used to study the electric properties of matter and the environment surrounding it. So the main topics are going to be to introduce electric charge, insulators and conductors, Coulomb's law, and electric field. I'm pretty sure I'm going to get to electric field today. We'll see. If not, we're going to do it on Wednesday, electric field lines. So we're going to cover all the materials needed for the lab on Thursday. So that's good. Okay. So many of you have done science in high school. So I'm hoping that you have done this experiment. If you haven't, I mean, basically what this shows you is how we observe static electricity. So pretty much what you do is you have pieces of paper on a table, and then you have a rod. It can be made of amber or plastic, it doesn't matter. And then you rub it with a piece of fur, like is shown here. And then what happens is that you can lift those pieces of paper because of attraction. That was the first sort of experiment or observation that we have that show us static electricity, which is basically the removing or the transferring of electrons from one material to another material. How? By rubbing the piece of fur on the rod of amber or plastic. So what you should know from physics and chemistry, right, is that the atom has a nucleus that has protons and neutrons, right? Which is why it's the densest part of the atom. And then you have electrons sort of like orbiting the nucleus of the atom. Nowadays, we know that they're not really orbiting. They are in what we know, as an electron cloud. But the first model, the Rutherford and then the Bohr model of the atom, they show the electron orbiting the nucleus, the positive nucleus, because they will model it as one proton and then one electron orbiting it. And why is that important? Because we use Coulomb's law and a bit of quantum mechanics, of course, to actually obtain what we know as the Bohr radius and the energy levels, which are the allowed positions for the electron to be due to levels of excitation, right? So when you study this before, or you have heard about electrons getting excited from one level to another, or doing an electron transfer, right? Or an electronic transition, sorry, from one level to another, that's basically due to an energy released or absorbed by the electron. But to model that, we actually use our physical laws, the understanding of how the electron actually orbits the nucleus of the atom. Now, of course, this only works for the hydrogen atom because there's only one electron and one proton. When we have more complicated atoms, like iron, for example, or carbon, it becomes more difficult. So that's when we start using the Schrodinger equation and all of these different models until we get to the concept of probability. But I digress, right? What you're seeing there is two situations that may arise in electrostatics. You may have repulsion or attraction. Like charges repel, opposite charges attract. That's the other observation that we have from static electricity. So that all comes into the concept of electric charge. So every object that you have and that is charged has a charge that is a multiple of the most basic unit of charge, which, as I showed you already, is a charge of the electron. The magnitude of the charge of the electron is given there, 1.60 times 10 to the negative 19 coulombs. Now, that is the magnitude of it. We know that for an electron, the electron has a negative charge and the proton has the same value, but positive. But whenever they tell you the magnitude of the charge, that's when we use the positive value of it, the magnitude per se. So we know that matter can be charged, and the charge of 4 coulombs gives you, or with a value of the charge that an object may have, you can estimate the amount of electrons or the excess of electrons or protons an anion may have, right? And this is what I was talking about, right? The electrons are in an atom as a cloud surrounding the nucleus. The cloud is negatively charged and the nucleus can be positively charged if there is an excess of protons. Now, the neutron doesn't have any charge, so it doesn't play into account for this. So then you're probably wondering, well, you have electrons and you have protons, so are they orbiting like planets around the sun? Sort of. That's why this was called, at the beginning of the 20th century, when this was all studied, this was known as a solar system model. And the reason why it stuck for a while is because it was a very simple, elegant, and it resembled what we knew about the universe. However, nowadays we know that just like with the solar system, the orbits per se of the electrons around the positive nucleus are not circles, but are more orbital ellipses. And they're not really orbits. They are just a cloud of electrons surrounding the nucleus of the atom. All right. And what's true, however, are the whole concept of energy levels. That's actually all right. That's correct. But we don't know exactly where the electron will be, as you know from the uncertainty principle, right? The Heisenberg uncertainty principle. So the idea behind this is that electrons are less massive and are normally free to move, especially in a conductor. The main difference between a conductor and an insulator, for example, plastic and iron, right, is that electrons in iron or copper or gold are free to move on the surface. So when you heat up or when you charge a conductor, all the charge stays on the surface, thanks to those free electrons. So if you were to remove charge per se from one object to another, like what happens when you wrap the amber rod with a fer, you are removing electrons or you are transferring electrons into the bar. So what happens if you transfer electrons into the bar? The bar has an excess of electrons, so it becomes negatively charged. If you remove electrons from the bar, then it's the opposite. You are removing electrons, so you are positively charging. So you are charging by conduction. See what I mean? Now, this has been replicated in the lab, of course, and the basic example is the pieces of paper with the wrapping of plastic. So if you have a positive charge and a negative charge, they will attract. That's how we know the experiment works. But all that is static electricity. We're just removing and transferring electrons. We still are not talking about electrons moving, like for example, in a cathode ray tube. Not yet. We're gonna get into that later. So those are important observations that we did to understand the whole concept of charge. And there you are, right? If you transfer electrons towards the amber rod and you remove them from the fer, that's what happens. Now, what about the overall charge? Well, you probably remember about conservation of mass and conservation of energy. You can neither destroy or create energy or matter. You can only transform it. The same is with charge. You cannot create or destroy charge in the universe. It can only be transferred from one object to another. So if the amber rod and the fer were neutral, then the addition of the negative charge and the positive charge of both objects after rubbing them will be 0 coulombs as well. That's the conservation of charge. All right. All right, I spoke about this already. And then, of course, we have the whole idea of polarization. As I was saying, right, matter is made of atoms, and in the atom we find the nucleus and the electron cloud. So can we polarize materials by using a charged rod? Yes, basically you are seeing it there. If you have a positively charged rod made of any material, and you place it nearby the environment of an sphere, it can be conductive, it can be an insulator. Then you will see that the atoms are distorted, where the positive charge will be pushed away from it and the negative will be pulled towards a positive charge rod. And then later on, we can use this to charge objects by induction without the using of contact, direct contact or conduction. All right. A conductor has electrons free to move in the surface of the conductor. This explains why during winter, when you touch metal, for example, the door handle, the doorknob, to open a room, you may get a discharge. Or when you touch your friend's sweater, you also get a discharge. Because as you move in a dry environment, because that's what happens on winter, right? Sometimes you will notice that it becomes very dry. Then electrons or you can easily charge objects in the environment. And when you touch it, since we also carry our own electricity, remember synapses, right? From bio, you can get charge, and depending on the type of contact, right? Meaning on the surface, it can actually hurt. Which is why I always recommend people before you touch metal during winter, you wanna rub against an insulator. So what I do when I open the door, you wanna rub your hand on the wooden frame of the door So you remove any excess of charge in your hands or body, and then you can easily open the door. All right. An insulator, however, is a material where the electrons are moving from atom to atom. And the thing is that they are all, in terms of distribution, they are distributed in the whole volume of the object. What do I mean by that? Imagine this is a conductor, right? So the plastic, imagine this was metal. If this was to be charged, or maybe this better, right? All the charge will be on the surface of this conductor. But if this is an insulator, this is an insulator, the charge will be the liquid. You see, the charge is distributed all among its volume, which is why the way electrons move is much more slowly than in a conductor. Okay, those are the main differences between insulators and conductors. Sort of what you probably discuss when you talk about conducting heat, right? The reason why metal conducts heat better than an insulator is because of the free electrons on the surface. Or as we say in chemistry, the free electrons in the outer shell. There are also semiconductors, which basically have properties in between a conductor and an insulator. All right. This can be changed with their chemical composition. We're not going to be talking too much about this, but in circuits, sometimes it's useful to have semiconductors.
It's better. Try it out next time you park and rush for them.
What was that? Oh. Okay, so these are all the overall properties that we observe when we study static electricity. Conductors, insulators, attraction, repulsion, charging an object. But how do we quantify all this? We quantify all this by introducing Coulomb's law. So I want to leave that in there, and let's explore this equation a little bit, and then we'll do some examples of it. So Coulomb's law gives you the value of the force between 2-point charges. Now, if you have studied Newton's gravitational law or law of gravity, that equation looks very similar, right? The force of attraction between the Earth and the Moon, or the Earth and the Sun, is modeled by a very similar equation. But the difference is that instead of charge, we use the masses of the planets, and instead of K, we use the gravitational constant. In Coulomb's law, we have that the electric force or electrostatic force is equal to K times the magnitude of Q1, the magnitude of Q2, divided by R squared, where R is the distance between Q1 and Q2. Units-wise, Q1 and Q2 have to be in coulombs, and R has to be in meters. What about K though? K is a constant. Now, in the book, they give you this as K. However, I'm going to let you guys approximate this as 9 times 10 to the 9 to make it easy for the problems. And those are the units for the Coulomb constant. Newtons meter square per Coulomb square. So this force is a vector because you may have magnitude of the force, but also direction, depending on how the charges are placed or where they are placed. The force is along the line connecting the charges. It can be attractive or it can be repulsive. Now, if you have two charges, you may have these situations. They repel, they attract, or they repel if they are both negative, negative to positive. But you may have multiple charges. So let's do an example that is similar to, you're kidding me. Let's show you a problem that is like this. 3, 2, and 1. Basically, problems where you have to use columns. All right. What I'm gonna do is, first, we're gonna do problems in 1 dimension, like this. And then we will do problems in 2 dimensions before we introduce electric fields. All right. So when I do the problem, if you have any questions, please feel free to ask. All right. So that's good there. All right. So to use Coulomb's law, you have to make sure that you are careful with the units, with the signs. You need to be careful. You need to be comfortable with vectors. A few things, by the way. Since we're talking about point charges, we are going to be using a lot of prefixes because we are dealing with very small numbers. Look at the charge of the electron, right? So since we're dealing with small numbers, right? We're going to be using micro and nano most of the times to list the value of the charge of an object. I can give you a charge, and I can say that this Q is equal to 6 nanocoulombs. But we need to have this in coulombs. So you need to remember, or you need to change that into coulombs. 6 nanocoulombs is basically 6 times 10 to a negative 9 coulombs. Right? I can also give another charge, Q prime, and I can say that's equal to 20 micro coulombs. Micro is 10 to a negative 6. So we just say that that's equal to 20 times 10 to a negative 6 coulombs. All right. So just keep in mind that in the textbook, in exams, and in the class, we're going to be using prefixes like that. All right. Okay. So let's give you an example on how to do a few of those problems of Coulomb's law. So example 1. On the x-axis, you're going to be given 3 charges. 1 there, 1 here, and 1 here. The value of the charges are going to be given like this. 4 nanocoulombs (10 nanocoulombs) and negative 5 nanocoulombs. See that, right? Yeah. Positive, positive, negative. And then I'm going to give you some distances. So let's say this distance is of 60 centimeters, 60 centimeters. And then this is 30 centimeters. No, 30, 20. The question you can be asked is find the charge, find the force, find the electric force vector at 10 nanocoulombs. So what is the force acting on this charge? All right. So we have to use the equation force equals to K Q1 Q2 over R squared. That's the electrostatic force. Now, R has to be in meters. Q1 and Q2 have to be in coulombs. And we know that K, I'm going to use 9 times 10 to the 9 Newton meter square over coulombs. And the values of the charge are in half, so I'm just going to use the magnitude of the charges. But we have to be careful though, because the electric force is a vector. So with the first step, when you do a problem like this, you want to draw the direction of the force. How? Between 10 and negative 5. Because this is negative and this is positive. They are going to attract. So this is my reference charge. So this charge is going to be like this towards 5. Because that's positive, that's negative. And I label this F1. Make sense? Right? What about 10 and 4? What about 10 and 4? They both are positive. Because they are both positive, they repel. So they are going to repel. So you're going to have a force here. Here. F2. Why do you need to do that? Because now you can see there in the screen, on the screen, that F1 and F2 are going on the same direction towards the positive x-axis, towards the east. That means that you are going to add them. You draw the direction so you know whether you have to add or subtract, like we did with the vectors at the beginning of class. So you have to add F1 and F2. So now the next step is to find F1 and F2. So let's find it. How do I find F1? F1 is between 10 and negative 5 by 8. Absolute values, right? So F1 is K, that's K, Q1 times 10 nanocoulombs times Q2, absolute value of negative 5, which is 5 nanocoulombs, 5 times 10 to the negative 9. Divided by the distance squared. And what's the distance? 20 centimeters by 8. That's 20 centimeters. 20 centimeters has to be changed into meters. 20 centimeters into meters. There is 100 centimeters in 1 meter. That means that 20 centimeters is 0.2 meters. Make sure you have that written down as well, okay? Your conversion between centimeters, millimeters, meters, also kilometers, that sometimes will show up. So 20 centimeters will be 0.2 meters squared. Make sense? Right? See the equation there? So this is what I was talking about. You have powers of 10. Well, 10 to the 9 with 10 to the negative 9 can be dropped by law of exponents. 50, 5 times 10 is 50, plus 9 is 450. So that will give me 450 times 10 to the negative 9. And 0.2 squared is 0.04. So now I just have to do that. So I reduce the expression. So 450 divided by 0.04, that gives me 112.5. So I get 112.5 times 10 to the negative 9 newtons. Like that. That's F1. Right? But I still need to find F2. Once I find F2, I can add it with this and find my net force. So for F2, what we're gonna do it here. Here, F2 is the same equation, 9 times 10 to the 9. Now F2 is between 10 and 4. So I have to do 10 times 10 to the negative 9, 4 times 10 to the negative 9, divided by the distance. Now the distance is 60. What's 60 centimeters in meters? 0.6. So that will be 0.6 square. Right? Now, I will just simplify this like that. 4 times 10 is 40, times 9 is 360. So 360 times 10 to the negative 9 divided by 0.6 squared is 0.36. 100 10 to the 4. So that gives me 10, 1,000. So 1,000 times 10 to the negative 9. No. $40, $9, $60, $50, $450.
Hey, Professor, for
Yeah.
for F1, would it not be 112.5 to 10 times 10 to the power of -7?
Yeah, that's right. So that's this 11250 1 2 3. So okay, this is 10 to the negative 6. It's just the same exponent here. Times 1,000, 1 2 3. So 11. This is 11.25 times 10 to the negative 6. All right. Thanks. That's the answer. So I made the calculator there, I didn't see it properly. That's the force value for F1, that's F2. Why do I do it like that? Because I have 10 to the negative 6, 10 to the negative 6. That's F2 also going to the right. Both are going to the right, as shown in the picture. Now you just have to add them. If you were to add them, here, F1 and F2, this number plus this number will give you 12.25 times 10 to the negative 6 newtons. That's the force at 10 nanocoulombs. Vector-wise, as a vector, it will be 12.25 times 10 to the negative 6 I newtons. That will be your final answer for that question. Okay. Now, you see, I use the equation twice because there are 3 charges. And I look at the force acting on 10 nanocolumns, right? So, I don't know if you guys have any questions regarding this. So at the end of the day, once you understand how to use the equation and drawing those vectors there, the rest is just your math, as you can see, F1 and F2. Be careful with the prefixes, be careful with the directions at the end. Now, in the assignment as well, they ask you to find the force on every other charge. So let's do one more. Let's find the force acting on on 4. Let's check what's the value of the force acting on 4 nanocolumns there. All right. Let's see. So what's the force acting here? The same equation as basically the same method, but we have to be careful with the directions. So between 4 and 10 nanocolumns, since they are both positive, they repel. And guess what? Look, if you look over there, here, this is the force acting between 10 and 4 nanocolumns. By Newton's third law, for every action, there is an equal and opposite reaction. So the magnitude of the force that I found over there is the same force that the charge of 4 nanocolumns is experiencing. You see this F2? This could be also, let's call it F3. They are not the same vector, but they have the same magnitude. Vectors may have the same magnitude, but different directions, different vectors. So F3, the magnitude of F3, though, I found it, is that 10 to a negative 6 newtons. Because it's the force between 10 and 4. That makes sense, right? But is that the only force acting here? No. There is 4 nanocolumns and also negative 5. But they are opposite charges, positive and negative. So they attract. So there is a force of attraction here. Let's call it F4. So we need to find the magnitude of F4. F4 is the force due to 4 and negative 5 at a distance of 80 centimeters, 20 plus 60. So here it will be K 4, 5 over 80 centimeters, which is 0.8. Any questions about that? I don't think so, right? I mean, it's the same. Now we have to be careful with this. 4 times 5 is 20, times 9 is 180. times 10 to a negative 9 over 0.64. All right, so let's double check this. Be careful with this. So we have 180 over 281.25 times 10 to a negative 9 newtons. That's my force between this and that. But F4 is going to the right. F3 is going to the left. So we need to subtract the values between these ones and these ones here. This minus that. So that's 10 to a negative 6. Let's use some math, okay? Because how do you subtract that value with that value there? That's 10 to a negative 6 newtons. That's 281.25 times 10 to a negative 9. So I'm going to take that number and I'm going to change the 10 to a negative 9 to 10 to a negative 6. How? How do you change this to 10 to a negative 6? This is a very important math trick. All right? Basically, what you do is you multiply this by 1,000. If you multiply this by 1,000, that's 10 to a negative 6. But then you have to divide this number by 1,000. So the number doesn't change. So this number is basically 0.28 times 10 to a negative 6 in 2 6 fixer. Yeah. Now I can subtract this minus that. Because if you think about it, this is like 1 times 10 to a negative 6, right? How about that? This is that 1.0, and then that's that. So this is going to the left, that's going to the right. So there is more force going to the left than to the right, because that's 1, that's 0.28. So what you write here is that's positive plus the negative of that. How about that? That will be your addition of those vectors. That will give you 0.72. Negative 0.72 times 10 to a negative 6 newtons, or magnitude wise, or sorry, vector wise, we'll have to do it on the x-axis. You can leave it like that, or negative 0.72 times 10 to a negative 6, or negative I newtons. Or you can say towards the west. Both are right. All right. But that's how you use columns now. When the charges are on one axis, on one dimension only. Any questions about this? That's an important concept. That's basically what you're gonna have to do at the beginning. The main difference between the examples here and the web assignment are the numbers. So be careful with the numbers they give you. They're gonna give you the same sort of units in terms of centimeters, micro or nano columns, all right? And I also noticed that there is a problem here. Normally the web assigns, I normally group them. So the first group from assignment 1 to assignment 5 or 6 are due near the end of July. Yeah, near the end of July will probably be due. The 26, 27, to give you time to study also for the exams. Now, that's for later. Are there any questions? All right. So let's talk about electric field. All right, and then with electric field, I will introduce forces and fields in 2 dimensions. All right. So what you saw today, or what you've seen so far, is how to point charges, because these are point charges, are acting when they are placed on a given situation or in a given arrangement, and how they interact with one another. Now, the concept of force is important, but where does this force come from? Why do they attract or repel? And why do they have those values, right? To understand that and to understand the motion of a charge, which is one of the objectives of this chapter, we need to introduce the idea of electric field. So let's show you what is the electric field. In the textbook, they label electric field like this. So you have electric field. And it's labeled as E vector equals to force electrostatic divided by a test charge Q. So the electric field is the value of the force per unit charge. The force is in newtons, the charge is in coulombs, which gives you an overall unit for electric field of newtons per coulomb. Now, the electric field is a vector, and it's a very important quantity, a physical quantity that we use to study the environment in which a charge may or may not move. Let's suppose I give you a charge here, and the charge is moving to the right. If the charge is moving to the right, there has to be a net force pushing it. Why? Because we know that the net force acting on a body or in a particle is equal to mass times acceleration. So this charge may be accelerated towards the east. Now, in mechanics, you study the idea of the force of gravity, friction, and so on. But if I give you a charge in an empty environment, in vacuum, for example, then the whole concept of friction is unneeded. Now, what about the force of gravity? Well, something that you should know, and please make sure you write this down, is that the mass of the electron is equal to 9.11 times 10 to a negative 31 kilograms. Furthermore, the mass of the proton is equal to 1.67 times 10 to a negative 27 kilograms. So what's the value of the force of gravity, mg? And do you think gravity will play a huge role? No. Gravity is actually the weakest of the fundamental forces of nature. So the electrostatic force, which later will be joined with the magnetic force to create what we know as the electromagnetic force, is actually more powerful, it's stronger. So if you have a charge in an environment, like here in a room, moving to the right, then the net force will be the electric force. That means that the electric force, this, is pushing the charge to the right. So if the acceleration is to the right, the force has to be to the right. Now, what do we see in this equation? We can rewrite this equation as the electric force vector equal to the electric field vector times the charge. Very important. What this is telling you is that the electric force, now we can find it by using the electric field. So the electric field and the force are parallel. If the charge, this is the thing now, this charge Q has to be positive. The test charge is always positive. So if we use that and that, then I can easily tell that the electric field is also going to the right. See what I mean? We know already from what we did before that there needs to be a charge with another charge to give you Coulomb's law, which is electrostatic force. Now what we are saying is that instead of worrying about the charge or the interaction between charges, I can just look at the interaction between the charge and the electric field. Now, who produces the electric field? Well, it's a source, and the source can be very far from this. So if I have the source charge here, as we go farther from the source, the electric field will get weaker. We are going to introduce the equation for electric field in a minute. For now, I want you guys to see the concept of it. You know what you can actually relate this to? Gravity. As a spaceship moves away from the Earth or from a body with a gravitational field, with gravity, the value of gravity, the value of the gravitational force becomes weaker to the point where that's why as we go in outer space, astronauts are floating, right? Because the value of gravity gets weaker and weaker. In the case of an electric field, it's the same. As we move farther from the source, the electric field becomes weaker. Now, I have that equation for electric field. Can I find an equation for the electric field due to a point charge? Well, yes, you can. We know that the electric force is equal to electric field times the test charge. Well, what's the value of the electric field by the source charge? The source charge is on the left and is giving this electric field. Well, we know that the electric force is equal to K, the source charge, the test charge, divided by some distance squared between these two. But wait a second though. That's equal to E Coulomb. The magnitude of E we can cancel Q's. And there you are. The electric field, the equation for electric field due to a point charge is KQ over R squared. Newtons per coulombs are the units. There. But that's the equation, and then I show you how the electric field works. What about what I showed you at the beginning of class with electric field lines? Well, that's the idea behind electric field. Electric field allows you to study the environment by understanding how a positive and also a negative charge emit electric fields. Let's use point charges for now. Let's use a positive point charge. So if I have positive Q, how do I emit or how do I draw the electric field lines due to that point charge? When it's a positive charge, the electric fields are radially outwards. So they emit fields like this. If the charge is negative, right? They don't absorb, but the electric fields are towards the charge. That's important when you are going to compute the electric field on a given region. All right. So the idea with mapping electric fields is to study the interaction between a positive and a negative charge, or also a positive and a positive charge. One of the most common examples that we use a lot in experiments and also in real life is the parallel plate. So here's where we get into more, realistic scenarios. A parallel plate capacitor, as we call it, right, is a device that has two conducting plates. Now, they are in 3 dimensions. I'm gonna project it on the board, and then you're gonna see also, you're only gonna see this. The thing is that one conducting plate is positive and the other one is negative. What we observe when we do the experiments on this is that the electric field always goes from positive to negative. That's an important property of electric fields. Electric field always goes from positive to negative, like this. Now, why does it go in this direction? Well, because as you probably have seen already, or you're gonna see this week, the way we trace electric fields is by using what we know as equipotential surfaces or equipotential lines, which are lines with the same potential difference. What's potential difference? Well, if you have used batteries at home, then you know that you have 1.5 AA batteries. That 1.5 is 1.5 volts. That volt is the potential value of an object. Okay, that's going to be more a topic of chapter 16. But just to show you here, the equipotential surface or line for this guy will be this. And what we have is that they make 90 degrees with electric field lines. So that's a situation that we have. The main thing that I want you guys to take from this is that the electric field goes from positive or negative and that we can trace electric field lines between positive charges and negative charges, depending on the geometry we given. So how about 2-point charges? Can we also do that? Yes. We can analyze the electric field lines between a positive and a negative charge. Now, you are going to do this also in the lab, but in the book, they show you this, and we know that the electric field lines go away from this and they go into this. So look at this. There you are. These arrows are important because they're telling you that the electric field is leaving positive Q and entering negative Q. Furthermore, we have 6 lines entering negative Q and we have 6 lines leaving positive Q. Why they are the same amount of lines? Because they both have the same magnitude of charge. If the positive charge was double, the negative charge, there will be twice the amount of lines leaving than entering the negative charge. So you will have 12 here, I don't know, 6. There is a problem like that in the assignment, so make sure that you are paying attention to this. Now, how do I know they look like this? Well, as I said over there, equipotential surfaces. Using a voltmeter in the lab, we can trace the electric field lines. One in the middle happens to be completely vertical. But then as we go to the right or to the left, this is what we find. We find that they become circular. And that if I draw a tangent line here, this tangent is the direction of the field, which makes a perfect 90-degree angle with an equipotential surface. I don't know if you can see there. Yes, you can. You see that? The same here, right? So that is how we investigate electric field lines. And this is why this is important. This gives you a better insight of how static electricity and how charges may move or may not move, which now brings me into another example, right? Can we use this in sort of an example? How can we use it in examples? Well, electric fields are used in different devices like the parallel plate to accelerate charges in motion, right? Or to stop them. So, yeah, we have time. So I'm gonna do one example. First with a charge in equilibrium. Now, how can you make a charge in equilibrium? We did a Coulomb's law today, and you can do it by having 2 or more charges. But if you have one charge, one object with given mass, can that object be suspended above the ground? Yes, you can use magnetic forces, which we're going to do later, or you can just use electric forces. So let's suppose that there is just electric fields. Can you have an object with a given mass, say 5 grams, be suspended on a given surface if there's an electric field? Yes. So let's show you the example. So let's say that you have a surface here. Right? And you have a mass of 5 grams that you want to make sure is suspended without any sort of motion above the surface. All right? What should be the electric field in the region? That's the question. Right? So if you have an object, and I'm going to say that it has 5 grams and also a charge, so mass of 5 grams. So you can ignore gravity now. You cannot ignore because it has 5 grams there. And it has a charge of, say, 20 microcoulombs. How can you, or what should be the electric field in this region? It's a problem like that in the textbook. Look, what you need to do is you need to think about the forces acting in this object. One of them is the force of gravity, the weight. So if you want this object to be in equilibrium, there needs to be a force acting upwards. And what force would that be? The electric force. So this has to be in equilibrium with this. In other words, the electric force has to be equal to the gravitational force. Now we know that the force due to gravity is mg. What's g? 9.8 meters per second squared. And what's the electric force? Let's write it here. The electric force is EQ. Right? That's the equation we're going to use that. Because we're going to find the value of the electric field. So this becomes EQ equals to mg. Now, if the electric force is going upwards, that means if that's a positive charge, that's positive, right? The electric field also has to go upwards. Now I can find the electric field by using that. E times Q, 20 microcoulombs is 20 times 10 to the negative 6. Equals to the mass, 5 grams. Okay. 1,000 grams is 1 kilogram. So 5 times 10 to the negative 3 kilograms. M times G. And then you want E will be 2.4 approximately times 10 to the 3 newtons per coulomb. So that's the magnitude of the electric field. What's the direction? Upwards. So the electric field will be 2.4 times 10 to the 3 newtons per coulomb in the positive y direction. Okay, so what have we learned on this? Before you guys start going, please, I have to take attendance, okay? So double check it. First of all, you can use the electric field in other type of situations that we didn't do before, right? Interactions between matter and electric fields. Next class, we're going to start with another type of interaction and charges in motion, by the way. electric fields can actually be very large. This is actually 2,400 newtons per coulomb. So that's another important property of electric fields. They can be very large. While we found with forces, they were very tiny, especially if the charges were small. So that's how we're gonna finish it today. I don't know if you guys have any questions, but honestly, what we did today, you can start doing the first 4 to 5 problems on the assignment. The assignment can be found in Canvas. If you go to modules, all right. Okay, let's see. So are there any questions?
I don't have any questions about the material, but the WebAssign isn't working for me. Like, I have the class on my dashboard, but every time I click on it, it goes to my previous physics class. So I'm not able.
You have to register with the code provided in the syllabus.
I did. It's in my dashboard, so I know it's there. I'm not able to access the actual course materials for the class.
Did you use the code I posted though?
Yeah, I did.
You did?
Yeah.
What's your name?
Ramya Radhakrishnan.
Ramya Radhakrishnan.
Mm-hmm.
Yeah, you are in the class. You may have to look at one of the tabs and go to like just double check when you go to WebAssign. Just make sure you click. It might be there. I don't know how you guys look at it, but I see you in the list though, in WebAssign.
Yeah. Okay. I'll just
go back
trying.
and see if you can, because sometimes you just have to change the book or the course or the code. So you are already registered. Yes.
Okay. Thank you.
Just double check that.
I'll try again.
Yeah, just double check and then send me an email. All right.
Okay.
Let me just don't go yet. I just have to double check. Some of you guys were not here. All right.